That's it for our presentation now, and I think we have received a couple of questions which we're happy to answer. I believe when I look at the overall amount of questions, we won't be able to answer all of them, but we'll go through and hope to satisfy those, and if not, we're probably happy to communicate even after the webinar on questions that haven't been answered. I think I'll pass back to Mike now to moderate us through the remaining session.
Thank you, Klaus and Sean. That was an informative webinar, and you're right. It is now time for the Q&A portion of the presentation. As a reminder to our attendees, you can enter questions in the panel in the left-hand portion of your screen. The first question we have here is the technology applicable to asbestos cement pipe?
Now, again, asbestos is a very sensitive topic. It has come up in the past. Now, we have had queries about such applications, and obviously our primary concern is for the safety of our operators. We really do have to evaluate projects on a case-by-case basis, whilst it is a wet environment, and as such, you don't have so much problem with loose fibers. The fact is you're installing a liner and there is movement within those pipelines. And so really we have to be very cautious about those sort of applications, and it's purely from the standpoint of operator safety.
All right. Kind of expanding on that, what are the access requirements? What type of access and access space is needed to perform a typical spiral wound rehabilitation?
Okay, well, we might throw between Klaus and myself for some of these questions, obviously, but the equipment itself is all designed to be able to be dismantled so as to be passed through standard access points. Typically we're talking as small as 22 inches, 550 millimeters, thereabouts. Standard manholes are typically 600 millimeters or 24 inches. And so we disassemble the machines, pass them through these manholes, down the shafts into the chambers where those machines can be assembled again. Now, space required within the manhole itself, the chamber, does vary. Obviously, with small diameter lines, you typically have very small chambers. You don't require a great deal of information there, a great deal of space there, but I'll hand over to Klaus for a moment.
Well, I think there was, we even received another question which goes to the same subject line. 24 inches the typical size of our manholes here and the manhole openings, and our machines are usually designed to fit through the 24-inch opening. Certain components, as Sean mentioned, will have to be dismantled, but it's a very easy process to fix them up together again at the bottom of the manhole. Especially the static winding machines where you have large size pipes, where we need a winding cage right at the bottom. The cage is typically the size of the diameter of the pipe or slightly smaller, and that can be dismantled and fixed back together at the beginning of the pipe.
In some cases, there will be some work required within the manhole. As Klaus mentioned, cage sizes may require a small amount of chop out and then subsequent reinstatement within the manholes, but this is a relatively quick process. I hope that answers the question.
Can you explain a little more on how the service laterals are reconnected after the spiral wound liner is used?
Yeah, absolutely. Typically, we're doing it like most other rehab technologies as well. The laterals will be locked by CCTV, I would say, before the rehabilitation process. For our technology, you have to imagine that we're installing a profile that doesn't transform its shape during the installation. So we need to know exactly where they are, and we have particular methods of how to lock the laterals before we line. And with that logging method, we can then identify the location of the laterals afterwards and open them up again. Once they're open, it's like any other technology, we always advise to seal the lateral with whatever methods are available in the market, whether it's Cosmic or Top Hat, or there are a couple of them that are applicable for CIPP, for example, and the same applies to spiral wound liners as well.
All right. Going back to the access discussion, particularly for the winding machine option, how much access space is required?
I think that was already covered just now, Mike, that access space is really typically the space in a manhole in front of the pipe is sufficient for the machine to wind, and all our components are built that they fit through a 24-inch standard opening.
And if we're talking about the SPR-EX technology, the small diameter technology, at the base of the manhole, that equipment is operated by a person, and so once again, we've had plenty of experience with this, and the typical manhole chambers, even at small diameter, are more than adequate for the expander equipment and the operator, one operator at that base of the manhole.
Right. At the beginning of the presentation, you mentioned the lifespan is generally designed to be 50 years. Is it possible to have a liner designed and tested for a 75 to 100-year lifespan?
Absolutely. Again, the one important clarification is design life and service life. The design life comes into the structural design, in which case we typically use an effective 50-year long-term stiffness. We have done the long-term testing according to ISO methods, according to the ISO standard. Now that's typically out to 50 years, but the data can, with a sufficient degree of correlation, be extended out further. We have, for example, I do recall that we have had one design where it required an 80-year design life as part of the design. And so yes, that can be readily done. It just requires a further extrapolation of that creep test data.
What is the maximum length that can be lined using with the SPR-EX?
Okay, the SPR-EX method there's a few little limitations there. It does depend on diameter, for example. At larger diameters, the profile is delivered to site on drums, and we do have one limitation in that we do not do profile joining yet with the SPR-EX technology. So there is a limitation according to the amount of profile that can be installed on a spool in the factory and then taken to site. Again, that limitation is primarily for the upper end of the diameter range. It really does depend on diameter and how much material is required to do that particular line. At smaller diameters, the limitation is not so much the profile capacity of the spools. It is driven by a few different things, such as the alignment and the amount of load back onto the equipment. There are ways to mitigate that load and reduce that load, but our experience has told us that at various diameters, such as an 8-inch liner, 200 millimeter diameter liner, I believe the maximum that we have done with EX is approximately a little bit under 600 feet, for example. We have done 600 feet, or about 180 meters, has been done at smaller diameters with the EX technology, as an example. Now, we do have some contractors that are challenging those limitations as time goes on. So that's not, as I said, it's not a hard and fast rule. A lot does depend on the liner, the host pipe configuration and alignment.
What is the typical reduction in pipe diameter?
Well, the typical reduction in pipe diameter, I think, it depends, of course, on the design. But our liner thicknesses start. We have probably six or seven profiles that we offer for different load applications and sizes of pipelines. But the thickness let's take an 8-inch liner, for example. We do have a profile which is called 85/7 there, and so that goes to a reduction in the thickness of the liner is then really 7 millimeters. But even there, we typically show an increase in flow capacity after the relining process.
So that was a 7 millimeter waterway wall. So the diameter is obviously reduced by, the waterway wall all around the pipe liner.
Yeah.
Can the liner provide full structural replacement of the host pipe? Yes,
it is designed in accordance with the ASTM standard, for example, to be, in most cases, a fully structural solution. Again, the ASTM does provide options for fully deteriorated and partially deteriorated conditions, but yes, it is designed to be a fully structural standalone liner. The ASTM standards do not consider any contributions from the existing host pipe. It is really all down to the liner to withstand the applied loads.
Is the 74 kPa the maximum internal pressure that can be resisted by the liner?
No, that's the requirement of the ASTM standard. Now again, the standards are for gravity flow applications. Now in certain circumstances you can have small pressures in gravity flow applications, but they are designed for gravity flow applications and not for pressure applications.
All right. Are there materials of host pipe that are not compatible with the PVC material?
No, they're typically not. So far we have not come across any examples of pipelines that are not applicable. I mean, we have typically you have concrete pipe, clay pipes, CMP, and we have lined them all, and we've had some more severe, badly deformed pipes as well, where we had to install our liner. But the material itself, and even earlier we talked about asbestos cement, it's not an issue actually. From an installation perspective and from a design perspective, it's not an issue.
For example, we have even done certain rehabilitation projects where there have been host pipe collapses, and there have been 3 or 4 lengths of the host pipe that have had to be removed, and we've wound the liner through that empty space without the support of a host pipe.
What is the Mannings equation for the liner once installed in a pipe?
The Mannings equation or the Mannings factor?
Mannings factor, sorry.
Yeah.
We employ a Mannings factor of 0.009. I mentioned during the presentation that we have conducted testing of liners at small diameter in both laminar and turbulent flow conditions. Our testing achieved values ranging from 0.008 to 0.0094, and we employ 0.009 to be consistent with industry expectations for plastic pipes.
All right. What is the amount of bracing required for the 216 inches during installation? Would that interfere with the flow?
No, it typically wouldn't. I mean, 216 inches obviously an extreme case where that's a real big pipe. But 216 inches, we would employ probably an 8-point or even more. I would have to check design calculations, but we need multiple points of bracing for the grouting process there. But the design of those brace frames has been developed to such an extent that flow still can go through. so it doesn't entirely block the pipe when we do that. I don't have any pictures now, obviously, for this webinar, but we can definitely provide some case studies there.
The other important factor to go along with that is it does depend on the particular technology that is being installed and the process by which you do the grouting. For the SPRTM profile, as Klaus mentioned, you'll have a multiple point of contact internal bracing. There are other technologies where simple beam and prop methods are used, and people do employ stage grouting to minimize the amount of bracing required. It really does depend on the product application and the host pipe, the design requirements there.
Continuing with the grouting discussion, we have a couple grouting questions here. What is the grout strength, and how do you ensure even grout distribution behind the liner for the SPR method?
Well, grouting strength is something Sean was alluding earlier on in the presentation as well. Depending on the design, we're using, sometimes we use a composite design, and in the composite designs we do partially rely on the strength of the grouting material. And here it really depends on design by design, but we have seen designs of 5,000 or even 8,000 psi. Now, grouting only applies to the SPRTM technology, and depending on the diameter, we are actually able to use the ASTM flexible pipe design as well in accordance to ASTM F1741. And if that's the case, we can also use cellular grouts with a low strength, and so there are different requirements depending on the project. But I would say typically if you go bigger than probably 100-inch, I would say that's the threshold usually where we have to go to high-strength grouting materials where the liner itself won't be able to absorb all the external forces anymore. And then depending on the size and the depth of the line, 3,000, 5,000, 8,000 psi. That depends.
Yeah, unfortunately, it's probably not a question that we can do complete justice to in the time frame available. So it really does depend on a case-by-case basis.
And quickly to the distribution of the grout, I think that was part of the question. How do we ensure that the grouting material sits everywhere? I think that's the same question that applies to all slip lining methods as well. We utilize grouting, multiple grouting ports to ensure through checking valves as well that the grouting material has reached every single level of the pipeline. It's hard to explain this now over the phone, but if you have done slip lining or any experience with slip lining, you can assume that we're doing the same thing.
Okay. This will be the last question for the webinar. Is there any maintenance cost to the liner?
Well, maintenance cost to the liner, I would say not as such, but I believe that most agencies, municipalities have their maintenance program, and that cost does not increase or because of our technology. I think it actually causes a decrease of your typical maintenance cost because of the flow coefficient that we are providing, and therefore no, there's certainly no additional cost.
If I can add to that, because it is one very important factor, after lining it is important what cleaning equipment that you do use. After lining, as with most liners, we don't recommend the use of mechanical cleaning devices, chain flails and rotor rooters and so on. We really do recommend water jetting, and we limit the pressure from those water jets typically to 2,000 psi. It really is important not to use mechanical devices within rehabilitated pipes.